Building a functional AI demo with a frontier model is no longer a difficult engineering challenge. An API key and a few hours of work can produce impressive prototype results. But as organizations move from pilots to operations, the primary bottleneck has shifted. The problem is no longer maximizing raw model capability. The problem is safely integrating that probabilistic capability into existing, highly constrained business environments. Solving this integration bottleneck requires a specific discipline, the forward-deployed AI engineer. Success in modern AI deployment means treating the large language model not as a standalone, omniscient solution, but as a single probabilistic component that must be tightly bound within a strict, deterministic enterprise architecture. This approach requires a different skill set than traditional machine learning engineering. A machine learning engineer focuses on the model itself, developing training pipelines, engineering features, and optimizing inference systems to push accuracy metrics from 88 to 91%. The forward-deployed engineer assumes the model already exists. Their task is mapping messy customer workflows, enforcing data isolation, integrating the model into existing enterprise systems, and proving measurable return on investment. This diagram illustrates the 6 operational layers top AI labs use to evaluate forward-deployed candidates. They test a mix of deep system design, deployment reality, and the ability to handle both technical ambiguity and executive communication. To see exactly how these layers are applied, we are going to engineer a production-grade 10-layer enterprise AI architecture from scratch. This structural discipline is the only way to convert an unpredictable text generator into a reliable, revenue-impacting business system. This diagram represents our architectural baseline, a single, isolated LLM layer. If we deploy this raw model into a business environment, we hit our first constraint. Enterprise knowledge is dynamic. Internal policies update, product docs shift, and customer records change daily. Fine-tuning the model on company data fails here. The moment a policy is updated, the model's weights contain outdated information, and retraining for every minor update is cost-prohibitive. To solve this, we add a retrieval layer and a re-ranking layer underneath the LLM. The engineering rule is to use retrieval augmented generation, or RAG, for knowledge grounding. Fine-tuning is reserved strictly for adapting the model's behavioral reasoning or output formatting. For the retrieval layer to reliably surface the right documents, it requires a hybrid search approach, combining traditional keyword-based BM25 with semantic vector search to ensure high recall across massive internal datasets. By decoupling knowledge storage from the model's weights, we allow for instant information updates without ever needing to retrain the underlying model. Giving the system access to an entire enterprise database introduces a critical risk: an assistant accidentally leaking confidential HR or financial records to unauthorized employees. We secure the system by placing an authentication layer at the entry point to handle single sign-on and role-based access control. This allows us to implement permission-aware retrieval. In the vector database, every individual document chunk is tagged with specific metadata defining its owning department, required role, and sensitivity level. When a user submits a query, the retrieval layer filters the document chunks against the authenticated user's permissions, passing only authorized text upward to the LLM. The overarching security rule is strict. The LLM must never receive unauthorized context in its prompt window. Data isolation must be handled deterministically. You cannot rely on a prompt to tell a model to ignore or hide confidential data it has already processed. Moving beyond answering questions, we add a tool layer so the system can execute actions in external applications like Salesforce or ServiceNow. We divide these APIs into 2 categories. Read-only tools allow the model to query an order status or check calendar availability without altering the underlying data.
Write or action tools carry significantly higher risk, enabling the system to issue refunds, send emails to clients, or modify database records. These action tools require strict architectural controls, including deterministic policy checks, item potency keys to prevent duplicate actions, and comprehensive audit logs. For highly sensitive actions, the architecture requires a human-in-the-loop step, halting execution until an authorized user explicitly confirms the action. Probabilistic models cannot be trusted to execute high-stakes business actions autonomously. Their outputs must be bounded by deterministic validation layers. This brings up a common professional misconception. that enterprise AI requires fully autonomous agents, capable of independent, multi-step planning. In production environments, fully agentic loops introduce high latency, unpredictable decision pathways, and the risk of cascading errors, where one hallucinated assumption ruins a sequence of actions. Instead of autonomous decision-making, we introduce a query router to classify the user's intent up front. The router enforces logic. Simple knowledge questions are sent straight to the RAG pipeline. Complex requests trigger pre-bounded tool workflows, and out-of-scope requests are rejected. To handle these rejections and low-confidence outputs, we add an escalation layer. If retrieval confidence is too low, the system does not guess. It seamlessly routes the query to a human support agent. Structured, deterministic routing is vastly safer, cheaper to operate, and easier to monitor than unconstrained autonomous agents. Finally, we complete our architecture with a guardrail layer. A foundational safety principle for forward-deployed engineering is that you never rely on the core LLM to police its own outputs. At the point of generation, we apply active defenses, utilizing grounded prompts that strictly require the model to cite its retrieved sources. After generation, a secondary, much smaller verifier model, or a rule-based checker, validates those citations, ensuring every claim is actually supported by the retrieved context. Enterprise trust is established only by layering deterministic, active checks over every single probabilistic output. A fully mapped architectural diagram is entirely useless, without rigorous quantitative evaluation to prove it actually works. We start with offline evaluation. Engineers build a golden data set of realistic, ambiguous, and adversarial user questions. This allows us to measure correct answers, score citation accuracy, and run automated prompt injection tests. For online evaluation, the system is deployed in shadow mode, running parallel to human workflows without full automation to test repeatability and baseline performance. This dashboard shows the dual telemetry forward-deployed engineers must monitor. They track standard software metrics like latency and token cost, alongside AI-specific metrics like hallucination rates and retrieval precision. Successful enterprise systems are shipped based on proven operational reliability and safety, never on the basis of a few impressive isolated prompts. The final hurdle of deploying AI is translating this technical success into clear executive communication and tangible business value. Deployments follow a strict 6-step framework: mapping the context, identifying constraints, designing the architecture, defining metrics, establishing a failure plan, and ultimately measuring the business impact. When explaining risks to non-technical stakeholders, the language must be grounded in business outcomes. We do not say the model hallucinates due to poor retrieval grounding. We explain that the system may produce unsupported answers and detail the exact guardrails in place to prevent it. True return on investment is proven by baselining current operational performance, such as the average cost and time to resolve a support ticket, and comparing it directly against the metrics collected after deployment. The ultimate value of the forward-deployed AI engineer is protecting the enterprise from both underbuilding and over-automating, turning ambiguous business problems into safe, measurable reality.